Good morning, one and all. Let's go back and let's again continue our discussion about Bayesian frameworks. Okay, so maybe I would quickly touch upon various important points that we have discussed as a part of this Bayesian framework-based classification. So first thing there is that you will be essentially let us just write some terminology there. Let your x bar be the feature vector, right, that represents a given sample of this BNL dimensional one. Then let there be m classes, and to one of these classes you want to assign a given feature vector x bar. That's the problem. Then what you would be in order to do that, the way you will do in the Bayesian framework is you would be computing probability of omega I given x bar. So these classes are represented by omega 1, omega 2, and so on till omega m. So you would compute this for all values of I from 1 to m, and pick that one which has the maximum probability. That's how you would decide that. And this is referred to as conditional probability or a posteriori probability. Well, you cannot right away compute that. You do not know really that. So how we do it is we do the calculations based on Bayes theorem, which tells us this will be equal to probability of x bar given omega I into probability of omega I by probability of x bar. Now, this term is referred to as, what is the first term referred to as? Meanwhile, I'll write this is PDF of x bar. What is the first term? Likelihood. And this is prayer probability. Now, we have discussed in detail on how P of x bar can be computed from the likelihoods and prayer probabilities. We have discussed given a training set, one possible way of computing prayer probabilities. We have also discussed one possible way of computing the likelihood functions, right? And then for the analysis purpose, we made certain assumptions and we have done different stuff there. For example, we considered there are two classes and did some analysis on that. And also in some, to draw some inferences and to get some intuition, here we have also made we began with some simple cases, then we started generalizing that. So anyway, P of x by, so as we mentioned earlier, it is the maximum posteriori probability when you consider that the prayer probabilities are equal, and anyway PDF of x bar doesn't depend upon to which class you are going to assign that. That's going to be same irrespective of to which class you would assign x bar. So with these assumptions, you're maximizing a posteriori probabilities will be equivalent to here there you maximize the likelihood functions if these are your assumptions, right? Then we would be computing it for different values of I, and you pick that which has maximum value. And then we have written an expression for error probability there in this, what would be the error that would be committing. So again, I have drawn it for L equal to 1 so that it is easy to visualize. Assuming that you have a distribution there, one for foreground and one for background, or you could say this is for probability of, this is, I'm drawing likelihood function. So let's say, what should I write here? X bar given omega 1. This is probability of x bar given omega 2. Okay, so then we have seen that let this this would be, so if you are taking this point, the intersection point here, that is something that minimizes the total probability error because after this, let's call this as x naught. As you could see, if you are after this, obviously the probability is coming from the class 1 or less than the class 2. So you would assign it to class 2. Before this, the probabilities, the likelihoods of class 1, this is the class 1 which is there on the top, is more than this. So that's where you would assign to the class 1. So you look at the x bar, and of course then you would assign that. This is based on the likelihoods, but in fact there is no reason why you should have all the prior probabilities equal. So taking that also into account, we have written the expressions. Let's call this region, whichever region from minus infinity to x naught, that as r1 here. Any region after this x naught to infinity as r2. Can you, one of you, quickly help me to write the expression for total error probability? In this case, total error probability is, let me first write for the error committed by that which actually belongs to class 1. So I would put R2 here. Can you help me quickly? Probability of,
Omega 1,
very good. Then
in
multiplied with
probability of
probability of,
x bar
uh, given,
over given omega 1
very good. This you are doing over region
dx bar
R2, right? Dx bar, very good. This is the one,
plus
yes, plus integral over,
probability integral
hmm,
over r1
hmm,
probability of omega 2
hmm,
into probability of x bar
hmm,
given omega 2
right.
into dx bar.
Very good. Okay, hope everybody is fine with this. We have discussed it in a couple of classes now. Then what we did, minimizing the average risk. See, this is not always enough for us, because misclassification from class A to class B in some cases may be acceptable, but not from class B to class A is not acceptable. Or at least you don't mind if some that belong to class 1 went to class 2, but you would rather try to minimize things happening from the other end. So in that context, what we did then is we have introduced something called as minimizing the risk, or minimizing the average risk. That's what we did, particularly in the last class, minimizing the average risk. So simple thing for these two, if you take it, for example, then the probability of error here is, for two classes, I could write it as, if something, let lambda 1, 2, say that it actually belongs to class 1, but it has been put into class 2, that you want to, let's say you don't want it. Let's say omega 1 belongs to a malignant tumor, and omega 2 belongs to a benign tumor. Lambda 1, 2 is penalty that you are going to impose if a malignant tumor is wrongly assigned as benign tumor. Lambda 2, 1 is the penalty you are going to impose if a benign tumor is assigned wrongly to a malignant tumor. So in this case, lambda 1, 2 and lambda 2, 1, what's the relation that you would like to impose? Well,
1
when
2
you want
greater
to
than 2.
impose, right, this you want to put greater than. So it's a simple modification here to achieve that. You just introduce here lambda 1, 2 here. Okay, so just in the interest of time, I would rather directly do that modification here. I would put lambda 1, 2 here, then lambda 2, 1 here. Okay, so that's how this one. You could see now I did not make any assumptions about prior probabilities of omega 1 and omega 2. They could be different, but there is still one assumption here which I need to generalize, is number of classes that are there. Okay, so then we have derived the expression for average risk when you have m number of classes, right? So how did we do that? Well, we started with the penalties associated with RK, we called it, penalties associated with each class. That's how we did it. Then obviously, then what would happen? Each class means something that belongs to a kth class, but has been assigned to another ith class. So all these terms for varying values of I equal to 1 to m, we have written those expressions. right? And of course, then there will be, for each one, they will be in the region Ra, this has been assigned, right? Then what we did, penalties associated, this whole express, the summation would give me the total penalty, that or total risk, whatever you may call it. Then we slightly rearranged those terms such that instead of class-wise penalties, we have region-wise penalties. That's all we did. We realized it's a linear relationship there. So maybe I would right away write this expression here. I'm sure by this time you are all clear with that. So what was that expression? R equal to summation of course, k equal to 1 to m r k. This is penalty associated with each class. We have written and then we rearranged those terms there. We end up with r equal to I equal to 1 to m. Well, integral over Ri is there over region Ri. Then there is a summation here, which tells you from k equal to 1 to m, lambda ki, right, into probability of omega k into probability of x bar given omega k into dx bar, right? Now this is what we did in the last class. This is still this is the point up to which we have done in the previous class. Minimizing this would be equivalent to minimizing each of these integrals, because anyway that's a linear one. You want to minimize each of those integrals. That's what the expression that is there. So for example, I am given an x bar vector. How do I do that now? And assume that I would assign it to an ith region. Okay, I would assign it to not ith region. I would assign it to a kth class here. How do I figure out to which class it would belong? I would compute now. This also we discussed. In fact, I would define a variable called Li, which is defined as k varying from lambda to m, sorry, k1 to m, lambda ki probability of omega k into probability of x bar given omega k into dx bar. So essentially, you would see that when it is assigned to a particular class out of those m classes, what is the resulting penalty? This you do for all possible classes varying from 1 to m and choose that class. You assign it to that particular class that has resulted in minimum penalty. Okay, so you do it and then we assign we assign x bar to, let's say, ith class where, let's say, Li is less than Lj for all values of j except the value of I. Well, this is maybe a little bit abstract now, and from this equation, we don't really will be in a position to draw some good inferences, meaningful and understandable inferences, and also to relate it with whatever we have seen earlier. So again, we will come down from this generalized expression to some specific cases. Okay, so let us now consider again two class problem. Okay, please hope you are all with me till here. Okay, now let's work it out now. Let us say m equal to 2 classes for me. Now, how many LIs are possible here? L subscript I, how many of them are possible now? L1, what is the value of L1? Just expand that summation and tell me what is the value of L1, isn't it?
1 1.
Lambda 1 1, probability of
Probability of omega 1.
into
Probability
probability
of
of
x bar by x bar
x bar.
given omega 1.
Very good. Then
Dx bar plus
No. There is, oh, sorry, this dx bar is not there, huh? Because these regions are all, that was a mistake. Sorry for that. See, this is just Li we are looking at a given point x bar. Where is it going to be there? What we are doing, we are assigning it to one of the class and then computing the class wise error. If you assign it to this class, what is the error contributed there? So there is just a summation there. Huh? So here the point is everything that is inside this, okay, this has to be minimum. This whole thing has to be minimum. This summation is what we are minimizing. Yeah. Now you tell me. Plus
plus lambda 2 1 probability of
lambda
omega
2 1 into probability of omega 2
omega
into
2 probability of
probability of
x bar
x
given
bar
omega 2.
given omega 2. Okay, this is what the penalty that is associated if you are assigning the given x bar to class 1. Okay, now similarly you tell me L2 now. Lambda subscript
1 2
probability of omega 1, of course the same thing will be there, is it not? Into omega 1 plus lambda subscript,
2 2
right, into probability of omega into probability of x bar given omega 2. Now, what can we say is, yes, if, okay, uh, let's say you assign it to class 1, if, when do you assign this given x bar, assign it means here this it corresponds to x bar. If, when do you assign it to class 1?
L1 is less than L2.
Right. If L1 is less than L2. See, there is nothing difficult here to comprehend. Look at the term L1 and L2. Consider even a simpler case. When it belongs to class 1 and it is rightly assigned to class 1, your typically what would happen, your lambda 1 1 is 0 there. Just to have it in a matrix form, when you have multiple classes, we have resorted to this kind of lambda 1 1 also. But when you are in lambda ij, when I equal to j, this is 0. Okay, so you just look at this. So you can ignore these two diagonal terms to get an intuition for it. All you are doing is, in fact, same as what you did earlier. If you take that assumption, the way you did earlier, it's exactly the same, except that lambda 1 2 and lambda 2 1 are there. And how do you take a decision? That is all we are doing here. Lambda 1 1 equal to 0, lambda 2 2 equal to 0. And can I say lambda I in practice, lambda I is less than lambda ij for all I that is not equal to j. Okay, instead of putting 0, maybe for some reason, even if you want to, yeah, we still keeping lambda I there. So all I'm saying is, the penalty that you are going to impose if it is wrongly classified will be obviously more than rightly classifying it. Okay, lambda I means it belongs to ith class. We assigned it to ith class, so error is in fact 0. Now I have purposefully written this trivial thing also I have written, which why I have written would become clear to you now after a couple of steps. So L1 is less than L2, then I will assign this to class 1. Okay, for omega equal to 1, I will assign that. Let's write that expression now. When do I assign that? Lambda 1 1 into probability of omega 1 into probability of x bar given omega 1 plus lambda 2 1 into probability of omega 2 into probability of x bar given omega 2 is less than lambda 1 2 into probability of omega 1 into probability of x bar given omega 1 plus lambda 2 2 into probability of omega into probability of x bar given omega 2. Right? Now, let us collect terms with similar probability terms here. So you could see these two are same, whichever they're just below this. So I would take them to one side. So can I write this as lambda 1 1 minus lambda 1 2 into probability of omega 1 into probability of x bar given omega 1 is less than, what is the, I want to take all the other probability terms on the other side. What's the multiplication coefficient here? You tell me in terms of lambdas first.
Lambda 22 minus lambda 21.
That's right. Lambda 22 minus lambda 21 into probability of omega 2 into probability of x bar given omega 2. Okay. Well, now it might be clear to you on why I have written this part explicitly. You could see here typically lambda 1 2 is more, and this you could consider it as 0. Okay, so what I would, so that, and same is the case here, lambda 2 2 will be less than this. So I would multiply both sides with a negative sign. What would happen to, if I multiply both sides with a negative sign, what will happen to this less than? This inequality, will that be still negative? Will that still be less than or something else?
So inequality
you-
will change, sir.
Right. What will that become?
So it will become greater than.
Right. So I'm doing that now. All I'm writing now is lambda 1 2 minus lambda 1 1 into probability of omega 1 into probability of x bar given omega 1 is greater than lambda 2 1 minus lambda 2 2 into probability of omega bar 2 into probability of x bar given omega 2. Okay. Now I will take the likelihood terms on one side and let's see what we are going to get. Hope you are all working with me. If not, please do that. Probability of x bar given omega 1 by probability of x bar given omega 2 is equivalent to, I can write it here as lambda 2 1 minus lambda 2 2 into probability of omega 2. What do I get in the denominator?
Lambda 1 2 minus lambda 1 1
Okay,
into
good.
probability of omega 1.
Right. This is, sorry, I should keep here greater than, right? I just moved it there. So this is when I would assign it to the class 1. And what are those terms which are there in the numerator and denominator of the left hand side?
Likelihoods.
Likelihood. So can you guess what this term would be called as now? We call it
Ratios.
as, that's all, likelihood ratio. Okay. Now, depending on the likelihood ratio for a given x bar, you can tell to which class it needs to be assigned to. If this is greater than the terms that you have on the right hand side, then you would assign it to class 1. If not means, what does that mean? It is less than, or in otherwise I could tell probability of x bar given omega 2, right? That way also I can tell. If you this, then if this is the case, then you would assign x bar to omega 1. So you could write it in whatever way you want. So if it belongs, suppose if you are getting this less than, I still want to make it greater than, so I will take inverse of it again. So I could say if p probability of x bar given omega 2 over this is greater than, what would be then? Then I want to write something where I would assign it to omega 2. What should be there on the left hand side now? Right hand side.
So lambda 1 2
Minus.
minus lambda 1 1 probability of omega 1 by lambda 2 1 minus lambda 2 2 probability of omega 2.
Yeah, it's just time writing. It's enough if you calculate one of them, right? If the, for either the first equation, okay, I mean either this or this, of course, one of them is good enough. If it is greater than, if you calculate the first expression, if the right left hand side is greater than the right hand side, omega 1, or else it is omega 2, to which you will assign it to x bar. Well, you might have already noticed here one thing, that we purposefully avoided actually computing the regions as such, because in this way to compute it is very complicated. That too, when you have your feature vector is in higher dimensional space L greater than 2, when you once go feature vector, and also your number of classes are increasing, it's not so easy to actually see the boundaries and in which boundary this X bar is lying. That's not a trivial thing to do. We have purposefully avoided, if you notice, in the very beginning, by rearranging your equation by a region wise and computing those results. So there will be in the next module. So in this module, to some extent, you will not explicitly, for particularly when you will do these calculations of region computation, maybe for like one-dimensional and two-dimensional feature vector sizes. But more than that, that's also we'll more see numerically and qualitatively. But in the coming modules, you would see in how instead of these regions, we will take one more monotonically increasing function or decreasing function of these probabilities. And then based on that, you would figure out to which, and then you will see to which region it would fall. Okay, that's how you do it. So for right now, we all that I want to say is we have cleverly, to say so, avoided computing explicitly what are the boundaries for each region, but rather we are doing it in such a way that you know the distributions, the likelihood distribution for class 1, you know for class 2, and you know what are the penalties to keep, and that's how you are computing it here. Is that clear? Are any questions so far? Now, let's consider some special case here to further analyze this equation. If every one of you is with me, I'll just I'll take a special case here, and I hope even if I made it small, you could still see that. Let's take a special case 1, where I would assume here to further get some interpretation to this equation. Okay, let me keep, for example, lambda 1 equal to lambda 2 equal to 0. Anyway, I already considered here a 2-class problem that's not required. Then let's assume that penalty for making a misclassification from 1 to 2 is same as making a misclassification from 2 to 1. Okay, so how can I say that in terms of, how can I express that in terms of these penalty weights? Can you tell me how does it reflect in
Lambda
terms of
ij is
lambdas?
equal lambda ij is equal to lambda ji.
Correct. Just you know the possible ij values also. You tell me in that now, because we already limited ourselves to just 2 classes now, right? So can you tell me in that?
Lambda ij is equal to lambda ji for
That means
I and
lambda
j
1 equal
belonging
to
to 1 and
lambda 2. Yeah, that eventually boils down to lambda 1 equal to lambda 2. Is it not?
yes, sir.
Yeah, good. Now let's compute this one. X bar given omega 1 over P of X bar given omega 2. What is its value now with this? Okay, maybe I will make one more assumption also here. Probability of omega 1 equal to probability of omega 2 equal to 1 by 2, of course, then. Okay, so now you tell me what would be the right hand side of that.
1.
Correct. So what is it boiling down to? Have you seen this? So what is it saying? If probability of X bar given omega 1 by probability of X bar given omega 2 is greater than 1, assign X bar to omega 1. Did we see this case anytime earlier? What is
We
this?
started with this case, sir, before giving weights.
Right, correct. So this is the case of total error minimizing. That implies this is exactly same as minimization of PE, total error probability. Is it not? When your lambda 1 and lambda 1 2 and lambda 2 1 are same. In fact, this also you could relax. Even if you keep that, we have written the expression with PW1 and PW2 also in the minimization of error probabilities. Is it not? Did we not write that? Yes, that's where you would compute this, of course, and then it's exactly, yes. So you see here, you would compute probability of X bar given omega 1 into probability of omega 1, you would compute. That would be your a posteriori probability. When you assign it to omega 1, you do it for omega 2, then select that which is more. Okay, which probability is more, you assign it to that class. So this is even relaxing this assumption, generalizing it to like p1 omega need not necessarily prior probabilities need not be equal, but this would be equivalent to minimization of PE. Okay, now let's do something else. Another special case we would get. Now this special case 2, I would say that I will consider is lambda 1 2 is not equal to lambda 2 1. That's what I would consider. So, well, if you look at the boundary below which I would assign to one class and the other class from this expression should have been already clear that it is at x naught, right? Where these two are, maybe I'll just draw it somewhat better than what I have drawn here. Just a repetition of what I have been drawing from last couple of classes. So this is the boundary x naught, below which you assign that to omega 1, beyond which you would assign that x bar, this is your x bar, right? Beyond that you would assign it to the class 2. Now let's assume that lambda 1 2 is not equal to lambda 2 1. Okay, then what will this equation would become? That's the another. So I am relaxing this condition now. They need not be equal. So I am going to penalize them differently. Okay. So let's keep omega 1 and omega 2 also in this equation. So then what would that become? Probability of x bar given omega 1 divided by probability of x bar given omega 2, if this is greater than, what is the multiplication constant there? Yeah, let me also write here some constant into probability of, so I would write here probability of omega 2 divided by probability of omega 1. Then you at least tell me now what is that constant with which I need to multiply, such that if this happens, I would assign x bar to omega 1.
Lambda 2 1 by lambda 1.
That's all. You just substitute here lambda 1 2 by lambda 2 1. That's all. This is lambda 2 1 by lambda 1 2. Let's again, just to see some interpretation on what is happening to the boundary. Earlier, it was the intersection point when you have when you are penalizing them equally and your omega 1 and omega 2 are same. Now let us see if your prior probabilities are same. Suppose further, this is the further assumption. Then when do I assign it to omega 1? I would assign it to if my probability of x bar given omega 1 divided by probability of x bar given omega 2 is greater than lambda 2 1 over lambda 1 2. Then what I do, I would give x bar to omega 1. Now let's again go back to one interpretation of class 1 and class 2 that we considered. Suppose your class 1 is omega 1 is a malignant tumor. Omega 1 is a malignant tumor. Omega 2 is a benign tumor. So which one among lambda 2 1 and lambda 1 2, which one you want to be relatively have a high value?
Lambda 1 2 should be greater, sir, because we want to penalize classification of malignant wrongly as benign.
Very good. Very good. Then if that is the case, lambda 1 2 is greater than lambda 2 1, then what would happen to this value? Will it be greater than 1 or less than 1? 1. For example, let's consider this as, let's say, 0.5, because this is less. Okay. So then what I do, if probability of x bar given omega 1 is greater than, let's say this, assume as, let's say 0.5, some number which is any number that is less than 2 is greater than 0.5 times probability of x bar given omega 2, then what you do, then you assign x bar to omega 1. Let's draw a plot here. This is my x bar, one distribution for me, another distribution for me. This is probability of x bar given omega 1. This is probability of x bar given omega 2. When both are equal, this was my, this is my separation plane for both the regions. That you can call it as a decision line, if particularly when your x bar is one dimensional. Now, will that decision line moves to the right or left now? So this is where you could say probability of x bar given omega 1 equal to probability of x bar given omega 2, isn't it? Now, will that line moves to the right or left? You tell me that. With this.
It will move right, sir.
Very good. It moves right. Consider this. See, suppose these are same, for example. See, from here, if you look at probability of x bar given omega 1 is less, but you are already making it by half. Say, let's say you consider, if this is not very clear, just you consider some numbers there. Okay. Both are same. For example, 0.5 is one, or maybe 0.6, 0.6 you consider. This is probability of x bar given omega 1, probability of x bar given omega 2. And when you are moving to the right here, which is reducing, in fact, question is this term reduces or increases as I move from this boundary line? It reduces, is it not? So that is becoming, you see this is, maybe I will draw it in a different color for you, as I have hit here. And as I am moving from here, this is reducing. So let's assume that is becoming 0.5. Okay. This assume that earlier this is 0.6. Okay. As I move, let me take one more color here. For this, when I am moving here, is the likelihood increasing, or from here when you consider, is that increasing or not? That value? No, it is increasing, right? So let's say this is 0.7. Now what it is saying, suppose my this term is half, so half of that if I take, this is for 0.25, right? What happens to this probability? This becomes 0.35, is it not? This is 0.35. Oh, sorry. This half is not multiplied on both sides, only for the second one you are looking at. See, your probability are the other side quantities, half of probability of x bar given omega 2. Okay, so this is 0.5 only here, correct? And here half of this you are taking, so 0.35. So still this has higher probability, even when you made a move somewhere here. So still, since this is higher, then half of probability of omega bar of x2, you will still assign it to omega 1 or omega 2?
Omega 1.
That's all. Correct? Very good. So this is, that means here, this is very intuitive, is it not? Because although this is highly high, have a relatively high probability, you don't want to take risk. If at all, even it has further more slightly less chances, you still want to assign it to the first class itself. That's why you are moving this boundary towards your right. This, in fact, we did it in the second class itself, but there is something new that we have arrived. Earlier, we did not quantify We could not quantify how much does that move. But now we are able to quantify that. So which is given by this lambda 2 by lambda 1. This is what we got. So if you want me to keep it more decision line wise, if you want to mention that, my decision line now, if you see it, is when the probability of x bar given, what do I have here? Look at this equation. Omega 1, probability of x bar given omega 1 is equal to a multiplication factor of lambda 21 by lambda 1 2, lambda 21 by lambda 1 2 into probability of x bar given omega 2. This tells me when m equal to 2 and my feature vector has just one element, this tells me where the decision line is. So decision line is at x bar equal to x naught, where you get x naught by solving this equation. Now suppose you consider the inverse. My second class is malignant tumor. My first class is a benign tumor. Then what would happen? My lambda 21 by lambda 1 2 will become positive. So then what would happen? This would move to the left. I could exactly tell now what is the x naught value. Are you guys clear? This is means at the end of this whole thing. Of course, we did quite a few things. You have got a generalized expression. And by the way, all those lambda values are represented as a loss matrix. Okay, this comes from other statistical signal processing and from other communications also, where you call it as lambda 1 1, lambda 1 2, and so on, lambda 1. If there are m classes, what would be the subscript here? Lambda 1 after that 1m. So this is lambda 2 1, lambda 2 2, so on up to lambda 2m. Last one is m1, lambda m2, and this is lambda mm. This is how you would specify the penalties through this matrix, and this matrix is referred to as loss matrix. And typically all your diagonal elements are equivalent to what?
0.
Right. You will not penalize if they are correctly classified, right? It's similar to something you see in confusion matrix and other things. Okay, this is the last matrix. For the convenience, you are still keeping those variables so that your notations and summations, when you write, it is easier. Okay, so we not only derived now the general expression, that's what we did, region-wise, region-wise integration of the penalty expression, but we also now are able to come up with a quantitative expression, mathematical expression that tells us where this boundary lies. How does it move? Earlier we had a qualitative intuition. Now you have a quantitative expression for that. Are things clear so far? Yeah, expression is only for equiprobable classes. Well, we derived the expression, a general expression, but from there to make any interpretations, inferences, and connect it to what we have did, a special cases that we have discussed in the last class, I again came to a special case here. Otherwise, I could have introduced the probability of omega 1 and omega 2 also. Then these Gaussians have to multiply it with those constant expressions, and then I have to do that. Then if I am not making any assumptions about lambda 1 2 and lambda 2 1, I cannot really tell you where it moves. So that those assumptions also, two assumptions I have taken and shown you that. Okay, hope that is fine. Well, then maybe I should stop here.